Okay, now we'll talk about moment on a beam. Go find out that this is related to shear. We're going to use sort of the same concept in explaining this. But I like to start out with the definition here as well too. What is the moment on a beam at any point? Well, it's the sum of the forces multiplied by the distances up to that point. All right? So, and it could be any point. It could be the point at 1 foot, 2 foot, 3 foot. We could do this as we step across the beam the same way we did with shear, but again, the definition is now different. It's the sum of the forces multiplied by the distance to that point. Okay? So, let's think about this relative to that same basic example we talked about with shear. The example had a 1,000-pound load in the middle of a 10-foot long beam. Okay? But now I'm going to apply sort of this definition of moment to it. And we're going to figure out what the moment is at various locations. So let's take, for instance, hey, I'll start out at the 1 foot mark here. You know? Here's my 1 foot mark right there, little free body. I want the sum of the forces multiplied by the distances to those forces from my point. So here's my point, the little red dot. What's the moment at the 1 foot mark for this beam? 500 what? Well, the units would be foot, and then this is pounds, right? 500 foot-pounds. And it would be a clockwise, it's going clockwise about that point. So again, if we kept the same sign convention we've been using, you might say clockwise is positive. Again, a sign convention is arbitrary, but you know, if that's, let's at least give it a sign convention. All right? So 500 foot-pounds at the 1 foot mark. Remember that. What would it be if this was the 2 foot mark? 1,000 foot-pounds. That's right, clockwise, and we're going to call that positive. What would it be at the 3 foot mark? 1,500 foot-pounds. 4 foot mark? 2,000 foot-pounds. What about at the 5 foot mark? Well, let's draw it out. We've got 5 feet here. At this point, we've got, and we're looking at this point, right? We've got that load in there. What's the moment? Does 1,000 pounds do anything since it goes through that point? Nope. So it's 500 pounds times 5 feet, 2,500 foot-pounds. Okay? So you can see here, you're building up 500, 1,000, 1,500, 2,000, 2,500. What happens when when your point is like 6 feet? Let's do 6 feet. What would it be then? Well, I got 500 times what? 6. That's 3,000 foot-pounds. But I got this one too. Now that was 3,000 foot-pounds clockwise, but I got 1,000 pounds doing what? Counterclockwise. So it's not, what's the answer at 6 feet? 3,000 clockwise, 1,000 counterclockwise gives me 2,000 clockwise. What about if this was 7 feet? And that would become 2. Well, it'd be 7 times 500, that's 3,500 clockwise. 2 times 1,000, so it'd be 1,500. So can you see what's happening here? Your 2,500 foot-pounds right in the middle, then your 2,000, then your 1,500. And you can go all the way back, but guess what it's going to look like for the moment diagram? Again, the moment diagram, we typically just put a 0 line there, give it a capital M, but it's going to go up And again, we said the 2,500 foot-pounds, and then it's going to go back down like that. Because, again, at 6 feet we're at 2,000, at 7 feet we're at 1,500. You can sort of see the progression. Okay? So that's sort of doing the moment diagram piecemeal. Okay? But there's a relationship between the shear on a beam at a point and the moment on a beam at the point. Let me draw the shear diagram up here. And I want you to see if you can see what the relationship is. So for that same beam, our shear diagram did something like this. Came up to plus 500, then down to minus 500. Our moment diagram comes up to 2,500, and then back down. Can anybody see the relationship there between the shear diagram and the moment diagram? Well, that's one thing. The moment diagram does start at 0, does come back to 0. Absolutely. Okay, so yeah, that's point number 1. But what about do you see any relationship here? Well, think about the moment. What was the definition? The definition was the sum of the forces multiplied by their distances away from the point. What's this value on the shear diagram? Well, what's the height of this shear diagram right here? It's 500, and what is 500? The sum of the forces, right? What did you say the moment was when it was 1 foot out? 500. How would you get 500 foot-pounds from the shear diagram here? Wouldn't it simply be just the area under the shear diagram? 1 foot times 500 pounds, 500 foot-pounds. What did you say it was when it was 2 feet out? The moment when it was 2 feet out? You said 1,000, right? Well, look at this. What's the area here? 2 feet times 500 pounds, 1,000 foot-pounds. The area under the shear diagram is going to be your moment. Okay, because it is a representation of the sum of the forces times the distance away from that force, or the distance away from that point. If you're not interested, you can pick off what the moment is just like what we did based on this, but if you're just looking for maximums, a lot of people just do the general geometric shape. So I got a rectangle, right? The rectangle's 500 pounds high, it's 5 feet wide. That's 2,500 positive. So my diagram must go from 0 to 2,500 by the time I get to the end of the rectangle. What about this rectangle? What's its area? Negative 2,500. So I must go from 2,500 pounds here. By the time I get to this rectangle and I add that on, I'm back down to 0. Okay?